सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै।
Last time we have seen how to model a mono-shot multivibrator, and this time we will start with right shift register, which we have seen earlier in the combinational circuits. And here we have a 16-bit register, and 15 is the weight of the bit, and that's MSB and so on. LSB is 0. And if you wish to have this register contents, you can get it out here as data out 1, and naturally 15 through 0 indicates the width of the register as such. It has a clock input, and once again we'll take only positive edge of the clock, and this being a right shift register, shift automatically implies that it is going to be right shift. And when shift is asserted, only then the shifting will take place at every positive edge of the clock. And this, when you right shift, this 15th bit is vacated, so this will be filled with a 0. This is the case with Verilog instruction as such. And you can reset the whole register once again by a system reset. Let us see what the contents before shift is. Let us say 1010, and after the shift by 1 bit, naturally 0 will be occupied here, and all the contents will be shifted by 1 bit, and the last 0 will get lost in the process. And we'll see how to implement this. We use once again an always block as such, and as usual we'll use assign so that we do the pre-computation, say in this case the right shift. This you are already familiar from our combination circuit. We are going to precisely use the very same thing. The shifting is actually done in the combinational, but we also combine a sequential here, so that the real system picture will be this combination. And here data out 1 is shifted by 1. This is the symbol for shift, right shift as such, as we had seen earlier. And if you want left shift, you have the arrows the other way. And we assign this to what is called next. We have the same name, and this implies next value is going to be this, and this value will be used within the always block when the clock really makes its appearance. That's at the positive edge of the clock. Once again, we have an always block at positive edge of clock, we take the action, or at negative edge of reset. And once again, we check the reset condition here. If it is 0, then only what we will do is we will preset rather. It's not resetting. We will preset with the desired value that you want. And notice that 16 is, once again, it tells what is the total width of this data, and this is 16 bits as we have said, so 16 is there, and you also need this quote here, and B stands for the binary, and what follows is the binary pattern as such, bit pattern, and you notice that one underscore is being used. This has no real meaning as such as far as the system tool is concerned. It simply ignores this underscore. It is only to facilitate ease of reading at the user level. Otherwise it has no meaning. Suppose had I put all continuously without this underscore, even then it is valid. But readability will be poor when you are dealing with zeros and ones. 16-bit reading will always be a difficult thing. It is only to facilitate reading at your end. And this is the comment for this, which says preset when the system is reset. We want to shift if that condition is not met. So we would like to shift the contents. So what we do is we check whether the shift is asserted or not. If it is asserted, then what we do is we just assign that data out one next. This is containing nothing other than the shifted value here, which was pre-shifted here. So notice that that's a combination circuit, so that will keep on churning and be ready at all the time. So when the clock strikes, it is always the correct data that you have here. And that's the reason why we just assign. This will speed up frequency of operation. That's why always all time-consuming computation are always done outside using assign statements, and we just transfer the contents when the clock strikes. And the comment is clear from this. And if shift is not to be done, for example, if shift is 0, this block will not be processed. So what we do is we go to the next, and here there is no if statement here, because this happens to be the very last of the series, and we just wind up with else here, and here it only preserves the previous contents. And suppose we don't want to put this, we are free to do, just give a semicolon there. We can have an alternate way of implementing the same shift register. What we have used is that less than symbol twice, and you can also use concatenation as such. For example, let us say very same example, we are just nomenclaturing it as 2 here instead of 1, because we are going to simulate later on, and we should not have the same name for different outputs as such, although they are basically 1. Concatenate here 0, because after right shift what happens to the MSB is we fill 0 there. So we put a 0 here, and then we separate by a comma here. It means this whole thing you should regard it as a single 16-bit as such, and the first bit we are forcing it to 0 by putting like this, and then follow it by the actual 15 to 1, because after right shift this 15 to 1 will go to the rightmost end as such. So in which case 1 bit will be the last, LSB here, and 0 is not accounted because we don't really care whether 0 is there or not. If you want to preserve it, you will have to preserve it by another statement as such, which we will be seeing in one of the future applications as such. And pre-shift write the contents of data out to register by 1 bit. So you give a meaningful comment as we have seen earlier. And once again there's a always block here, and we take action only on positive edge of clock or negative edge of reset. So once again there's a begin, and finally there will be an end wherever an always block is there. Now we again inspect for reset being active. If it is so, what we do is just preset as we had done earlier, and if shift is asserted, then assign the shifted data here. This is precisely the same thing as you have already considered, and don't shift here, just preserve the contents. The next example we'll be considering is, suppose we have a parallel data as such. We want to serialize this data. So what we do is we can use a combination of shift register and counter. So this can be very easily implemented, coded in Verilog as such. And let us consider this block diagram. And we are not explicitly showing a shift register or counter here, but we can readily incorporate it in the coding as such. So let us say we want to once again reset the system with a power on reset or system reset, and you want to load a particular value at any point of time. You can assert this load, and prior to that you can set the data using this bus, say 15 through 0, that's 16 bits. That's what we stated earlier as far as the width is concerned. And so the output will manifest here. This will be a serialized output, it's a single bit, and when this is valid, that also will be indicated by another signal which is data valid. If required, we can use this. If it is merely asynchronous, you are not really bothered about these two signals. And when the conversion is over, you have to have an end of conversion sort of thing. So we give one more signal here as end of conversion. And so coming to this, if we have seen load, it loads the set data as such into the shift register, which is 16 bit in width. And when shift is asserted, and we, only then the shift will take place. The shift can be either right or left, and for that also you need one more bit of information, and that is this signal. So R stands for the high actually, as indicated here, and this is left. L stands for left. Left I have put underscore n, as usual the same notation we have followed earlier. So we can, if it is low, it will be left shift. So depending upon that and shift, we will take action accordingly. And positive edge of the clock is reckoned here once again, and we'll see how to implement code it. Once again, we use an always statement because all sequential circuits are represented by always with a positive edge of clock and so on. So once again, if a reset is asserted, we initialize all the outputs as such. We have a data out and data valid signal and end of conversion. All of them must be deasserted, and that needs no explanation as such. And if load is asserted, then what we have to do is we have a shift register inside, which is 16 bit in width as such. We don't have to put the bit here, although it is a good practice to put here. And what we need to do is we need to take the set input, set data input, what we have seen earlier here. This will have to be read and put into the shift register as such. That's what this statement is doing. And mind you, one statement is complete only with a semicolon. And you can put any number of statements here in the same line, or you can fold it just to save space to show in a single slide. I had done put it in this fashion. And once again, data out, we don't have to assert right now, because data is not going to be out right at this stage. What we are doing at this stage is merely loading the preset value. That's the set data as such. And we have a counter to keep track of how many bits we have sent. And since we want 16 bits to be sent in total, we will just initiate this one counter. This is 5 bits as such. So 16 is loaded onto that here. It's a preset value. And once again, you deassert all the outputs here. Next step is if shift is asserted and also the counter is not 0, which implies that it has been processing, sending the information. And so if it is not asserted, this is once again an AND symbol, and this is a total logic expression, and therefore you see 2 equal to. If you put 1 equal to, it will complain, 2 will complain. And here the reason is also if it is not equal to, you can use in this fashion. We have already seen here. And mind you should not use the tilde sign like form symbol. You should not use that here. In logical expression, only this exclamation mark is to be used. And if both are satisfied, then what happens, this thing will return 1 and this will return 1 if the conditions are satisfied. 1 and 1 will be 1 finally. So the total ANDing operation result only will be returned here, and it will be sensed accordingly. And if that happens, the condition is satisfied, what we have to do is do the shifting actually. And while shifting, we have to take care of right shift and left shift. So we have already seen the mux implementation as such with a question mark here earlier, and that's precisely what we are using now. We had to take action if the select pin is RL underscore N. If it is high, it means right shift. So that's what we are doing here. So remember that for mux, 1 input is here and 0 input is here with a colon and of course termination of this statement. And this one, if this is not satisfied, that is if it is left shift, it has got to be left shift by 1 bit, and that is the symbol here. And this is either this thing is assigned to SR or this one is assigned to SR. Here is right shifted content, here it is left shifted content. So that's what goes to SR. SR once again is 16 bits, therefore this result is also 16 bits, each of these results. Whereas this is only 1 bit, and the comment says the appropriate thing here, register the shifted contents. And next what we had to do in the same block is, same else if block, data out we had to take care. This is the data which is going out right now. So what once again you use the same RLN symbol here, and if it is right shift, what we need to do is we had to take the shift register LSB content, which is SR0, and output that, just assign it to this, transfer this contents into the data out as such. And if it is left shift, naturally this will be taking force. And here you assign the MSB here. 15 is the MSB, please note that. And SR within brackets, you just give specify only that particular bit. That means this is a single bit as such. So I think this is clear to you. So that's what the comment says. Select either LSB or MSB, of course depending upon whether this RLN is 1 or 0. And having done this one, we should not forget to decrement the counter, because we started with 16 earlier at the reset time. Now let us that 16, when it has decremented, it would be 15. But we are not going to check this status right now. We will check only later on. Right? We only take the action. Suppose had the counter been 1 instead of 16, 1 minus 1 is 0. So 1 bit is already processed here, and it naturally exits the entire always block as such. In the case where counter reg was initialized to 1 as such. And so this is to keep track of the bits to be sent. So how many bits are remaining to be sent will be known if you just inspect the counter reg. And one more thing we had to do is this data we are going to send right here. That means we should also send a data valid signal here. That is what is being sent here. And since end of conversion is, it's not really over, because there may be more number of bits to be sent. So we still deassert that. Once again, if shift is still present and the counter value has touched 0, which implies that all the 16 bits have been already sent in the earlier block that we have seen. So this will take effect only at the next clock pulse. So earlier clock pulse, all the 16 bits are already dispatched. What we have to do is please correct that. So end of conversion must be 1 here. So that's what implies here. And in fact, I have forgotten one more thing. One else statement also I have forgotten. So you just take it as after the end you have one more else statement, and you don't have to take any action as such. So you just put a semicolon and wind it up. See, we have end of conversion. So it is written there 0. It must be corrected as this. And then what follows is one end. This is corresponding to the end of the begin in the right on the second line as such. And then you have one more end because we started with one more begin right at the top after always statement. So corresponding to this end. So we have also to add one else because we are not accounted for that. So that else is put here. And since we are not interested in outputting anything, you just put a semicolon, implying that it's a null statement as such. So this we'll have to incorporate. So next we'll consider how to model a state machine as such. Now let us say we have 4 state machine, and in each of the states you wish to light up an LED or a lamp as such. So Z stands for one lamp, Z0 stands for the S0 condition state indicator. If you are in S0 state, then this lamp will glow as such, and likewise in all other states. And this S0 is the state, and in binary notation we can say, let us say it is 0 0, then 1 0. After this it goes to second state, and then after this, depending upon the inputs, it will go either to S1 state or S3 state as such. And coming back to the first state, if we have 2 inputs as such, and based on these inputs, all this transition will take place. And suppose if it is 0, input 1 is 0, so what you do is you continue to remain in the same state, and of course this will be lit. And when in 1 is 1, it will go to state S2, and thereafter it will go to either S1 or S3 depending upon this into input as such. If it is 0, it goes to S1, otherwise to S3. And once you land up in S1, again it depends upon in 1 and in 2. If it is 0 1, note that this 0 1 is same as this state, and it remains in the same state as such. And if it is 1 1, this happens to be 1 1, so it takes you to this state. And once again from here to and fro you can shuttle if you wish, and depending upon this control and this control. 0 1 once again is same as this 0 1 condition. And in either of these cases you can return back to the first initial condition state by depending upon into value, right? And let us see how to implement this. So once again we use the always block, and positive edge of clock, negative edge of reset, and as usual the reset. Here in this case there are 4 lamps as such, so we'll have to light them up, and all of them are initialized to 0, and this is deliberately done for the time being, because in S0 state this one will be lit. So we just it doesn't really matter, because the moment you reset it will go to the S0 state. In S0 state we have initially appropriately done that, so that will take care of itself. And we have another variable called the state, which is same as S0 mentioned earlier, or 0 0, that what we have already seen here. So this is S0 or 0 0, right? So that's what we are initializing here. So in this initialization, once again note that this is a non-blocking statement. Always within the always block you have to use this meaning it is equal to. Only in assign statement you have to put ordinary equal to. And note this one, this is reverse apostrophe as such, used here to indicate that it's a string. You can consider this as a string variable as such. S0 is the normal nomenclature, a valid name that you give. So it need not be S0, it can be even state 0 or whatever you want to give, you can give here. And every line is terminated by a semicolon. So we initialize when the system is reset, and one begin was there, corresponding end. Now what we have seen is earlier in the earlier applications, so many else if used. Here we have only one if and then else, and here starts a case statement. It's similar to what we have already seen in the combination circuit, and that depends upon the actual state, which is a variable here, indicating which state we are in. And if the state happens to be this S0, then only this block is executed. Similarly, you have for different blocks for different states as such. Once again, a group of statements will have to have begin and end, and we set the outputs 0 through 3 depending upon which state it is in. So we for S0 we want to turn on Z0 LED. And now in this case, suppose we say in 1 is 0, that's what the first condition is. If it is 0, we have to remain in the same state S0, that's what we have seen. And if this is not satisfied, that is in 1 is 1, then only you go to the second state S2. And nowhere in2 is brought here into picture. That means it's a really don't care situation here. It depends only upon the in1 and not upon in2, because we cannot put that. Right. And suppose we, after this, let us say it goes to this condition is satisfied, and if this condition is satisfied, we continue to remain every time the clock strikes. You come to the same route and are always revolving around the same state, right? And only if in1 changes to 1, this will not be processed, and it will go to the next state, which is S2 here. And so in S2 state, it is precisely same, except that Z2 is lit here. And in this case, we need to inspect in2, and based upon whether it is if it is 0, we go to the next state, which is S1 here. Otherwise, we go to another state S3. In S1 state, it is once again similar to this, and 1 is set for Z1 as such. And once again we inspect in2, and if it is 0, we take back to S0 condition, and if in1 is 1, then we go to S3. Please note that at this point when it enters, it implies that in2 is 1. If in2 is satisfied, this will be satisfied, and it will exit this block. It won't come to this. So that's what I was saying, if else, if they have this vetoing power, that's a priority can be assigned in this way. So if the top priority is met, it merely exits the always statement as such. And that this implies that in2 is 1 here. In2 is 1 and in1 is 1. If this condition is satisfied, it will go to the S3 state. Please note that it won't go to the this state, S3 state, immediately. It will go only at the next clock edge. It only prepares the ground to go for the next clock here, right here. Right? This will become very clear to you if you see the timing diagram while we simulate the whole thing. And finally, we use one else, and because all the conditions that we want to meet have already been met here, and so whatever doesn't meet, is actually in1 is 1 here, in2 remember is 1 here, and in1 is 0 here, then only it will come to this state automatically, because the other state is taken care here. So what only state that remains is in1 is 0, which will naturally take it to S1. And suppose here, from here we have landed up in this state, S3 state. So similar thing follows here. So we once again turn on all LEDs off except for Z3 here. In fact, you turn on here actually. And if you forget to turn off the other things, it will be considered as a register and remains in the previous state. So you should not forget to do that. And if int2 is 0, in this case we are in S3 state, so it will take you to S0. Otherwise, if that is int2 is 1, then in1 is 0, it will take you to S1. And if this is also not satisfied, that is in1 is 1, it will take you to S3. And we have also put a default, although it's not really necessary here, because we have in 2 bits of state we have only 4 possibilities, 0 through 3 here. And then why default? It is not just customary. Probably it may so happen that tri-state Z or don't care situation arises. It may not arise in a sequential circuit, but it's always safer to put here. And another point is you may have instead of 2 bits you may have 3 bits, in which case you have used only S0 through S3. So S4 through S7 are not utilized. So what will happen to such cases? So you should take that into account as such. So only then we can it will be trouble free as such. And then we started with case, so there must be an end case here, and we also started begin after always, so this end accounts for that. For example, let us say int2 is 1 here and in1 is also 1, both are 1, so it should naturally take you to S3, right? Say we are in S3 state, and in S3 state, let us say int2 is 0 here, but when you come here, it implies int2 is 1, otherwise it can't come enter this point. So then here also, if this is to be processed, this is the condition to be met. So if you are to come here, you had to have in1 equal to 1. That means to say when this is being executed, so it has to be in2 as well as in1 1. So let us verify that. So we were in S3 state here, right? When in2 is 0, it returns to, do you remember this? Okay. Anyway, what we found is in2 1 and in1 1. It should continue to remain in S3 state, right? If int2 is 0, it returns to S0 state. This you can verify once again. You can see this, and right? We are here. It is here. If int2 is 0, that is the top priority we have given. So it doesn't really care for in1 thing, right? That's what we meant right in the beginning. So if it is 0, straight away take to S0, right? I'll work out another example which you have already seen, that is pattern sequence detector as such. So we have the pattern sequence detector here. We wish to find the pattern 0110, and this is exactly same what you have already seen. And I don't have to go into this, I think, as I'll start writing the program as such, or you want me to explain this? Okay. So only difference is, earlier you had used the notation S0, S1, and being a binary bit here, 2 bits here, right? So I am dispensing with binary and even state as such, I mean S0, S1, which we have seen in earlier example of sequential machine. And here we straight away put a decimal number 0, 1, 2, 3, and the arrows indicate, and this is the input here. First one is the input, and output is this. That's all you had to remember. And another variable is the state. So you have, as far as the output is concerned, you have just 2. That is, one is out, which is single bit, and state is actually 2 bits, because it goes through 0 through 3. 3 means in binary it is 1, 1. So you need to keep track of that. While writing a full-fledged code as such, you have to have remember all that and get it reflected on the code that you have. And let us start writing here. And before we write, let us take the input pattern as applied as this. Say all 1, 1, and it may not be the very same example that we had taken earlier. and any pattern is good enough because this is a machine which should cater for all sorts of bit stream as such. So now if you inspect here, and this is the output decide, and what we want is all of them zeros so long as the decide pattern is not got. So the very first encounter with this 0110 pattern is here. It's all underlined here, I mean rather lined over the top, and 0110 is encountered here. So right at that point of time we want to put it 1 here, and once again this 0110 will produce 1 here, and 0110 once again will produce 1 here. And now let us write the code for this. Say once again we use always block, positive edge of clock or negative edge. Notice that there is no semicolon, I should remember that. So once again we will have begin and finally end somewhere. So lest we forget, I just put it here. Now what we have seen is we have to account for 4 states 0 through 3. So this is going to be, first what we have to do is there is no, reset signal is not shown there, but I have incorporated in the program. So first thing we have to do is, if reset is encounter, what we have to do is, there are 2 outputs mind you, out as well as when you reset, out must be 0, right? That's what we have here in this state, and the state itself must be 0 once again. So we will put this state here. Right? So begin and one end here, and we have covered the reset portion. So if not, that is else, what we should do is keep on accounting for each of the states. There are just 4 states, so we will use a case statement here. And the case depends upon the actual state here, right? The state is only decimal number for ease of writing. Note that this is not a capital C but ordinary C, because Verilog is case sensitive, so you have to take care of the case. So whereas VHDL is not case sensitive, right? That's the difference between VHDL and Verilog. And if state is 0, let us say this case we are going to put one after another. If it is 0, it means state is 0. Then we take this action. Now once again we will say begin and put, what do you want here? Out must continue to be in 0 only. Then what should happen to the state? Okay, we will put the state here. What should happen to the state? Now let us see. It all depends upon the input condition, right? So this is actually when you enter this, we are in state 0, but what you are going to write here is the next state as such. From this state, where do you go to? So that state is what is implied here, and that will take effect only with the arrival of the next clock. With the present clock arrival, we are here. With the next arrival, this will be taken into account as such. So state will depend upon in. Suppose in is 1, right? We need to stay right at state 0. Otherwise, we need to go to state 1. That's what is implied here. If it is 1, you remain here. If it is 0, you go to state 1. So this is once again a case for using a mux as such. So what we do is, what is the selector pin here? That is nothing but in. So we will put in, then question mark. So now it's a very simple thing. You just see, it has to go either to, if it is 1, it has to remain in the same state. So what we just put is 0 here, then colon and then 1. It's quite simple like this. Are we clear? Now let us try in the same fashion here for and there must be one end. So for case 1, now let us see. Once again begin and finally end. And here in this case, out must be once again 0, right? That's this one, right? And if the input is 0, it continues to remain there and that. So now what we do is state is, you can write right here, in, then question mark, then what we have is, if it is 1, what should happen here? If it is 0, it should remain there, right? If it is 1, it should go to 2. So we start with 2 and then colon 1, right? End is already there. Similarly for 2, once again begin, end, then out. Here also it is 0. Then state here is we are in state 2. So that is this state. So input is 1, not this. This is the output. So if it is 1, you go to state 3. So it is 3 here. And otherwise it's no here, right? So 2 to 1 you go. This is the input, and this corresponding output is same linked to that state. So we need to worry only about this input. If input is 0, we go to state 1, right? So the final thing we can write on similar fashion. Now let us take care. Out also will change. Then now we are in state 3. So depending upon the input, let us say input is 0, then you have to go to state 1 as well as set the output 1. So on the other hand, if it is input is 1, output is 0, and then it has to go back to this. Let us take this condition first. So we'll take just the output. If it is 1, once again here you had two conditions. It's a conditional output as such. So you had to once again use the mux. And again select pin is in. If in is 1, that is this one, right? And what you should have is output as 0. So if it is first one is corresponding to 1. So the output, we are dealing with output. So we are just assigning 0 here. And if it is 1, so what is the output? For 1 it is 0. For 0, this is the condition, right? In 3, we have in 1, 0, sorry, that is this. If it is 0, the output is 1. So it has to be 1 here. So what remains to be done is only the state. Once again, based on in, you take action. Now you see from 3, you can, if it is in is 1, so you can go to 0 state. Right? We are in 3. From 3, if it is input is 1, you can go to 0 state. If input is 0, you go to one state here, right? So that's what we put here. So finally we say an end here, and there was a case here. So what we had to do is write one end case also. Right, and have it taken off all begins ends. You can each of these blocks there must be a begin and end, and finally there must be a case. It's a counterpart end case, and then coming back here, this begin end is already covered here, and there is one more begin here. We said we will put one more end, that is this here, or you can just say right here. Right. So you can actually take this and go through this. You can take an input pattern and go through this and convince yourself whether the code really does what is intended to do. And this is clear, I suppose. So either 0 is assigned to output or 1 is assigned to output. So is the case for here. State is assigned either 0 or 1. In case where it is 3, let us say, you need naturally 2 bits here. So state is 2 bits in width, whereas out is just single bit. So or we'll see one of the patterns, probably at least for 0, 1, 1, 0. Shall we consider all of them were ones, let us say. So what is happening here? When you reset, it takes you to the state 0, and if let us say because it was 0 in the first clock pulse arrival, what happens, it initiates this, and once it has done this role, it has no more role to play here beyond that, right, because it's a priority encoder. So it takes you out straight away out of this always block, right. So next action will be taken only at the next positive edge of the clock, right. So with the arrival of the second clock pulse, second instance relatively speaking, so once again it will see. Now let us say the reset has disappeared, right. What happens? This will not be satisfied. So this is not executed, and this is therefore executed only one time at the power on condition, right. When you switch on the system, so there will be a pulse created and that will reset. And so long as it is asserted, that long it will keep on rolling, no matter how many pulses have lapsed. It will keep on doing this and get back, right. If there are 100 clock pulses, naturally 100 times it will revolve around and do only this. That the role is only to make out and state 0. That's all it will do. And beyond this, after the reset is removed, only then it can come to this portion. So having come here, it was already initialized to 0, the state. Therefore, naturally it will go to this block, execute this block, and then again exit without bothering about any other states there. That's what we said, it is a priority encoder as such. So here in this state what it does, again it depends upon in there, right. So if in is 1, right, we said that 0 will be assigned. So the state is going to be 0, but we are already in 0 state. So it continues to be in 0 state. So first, let us say some nth clock it has entered this for the first time. And it says state will be once again put to 0. So with the arrival of the next clock pulse, so it will again come to the same state, and it continues to be in the same state so long as in is 0, 1, right. Suppose in is 0. Then what happens? State will get updated to 1 now. So that's what we have here. See, right? From state, if the in is 0, it has gone to 1. And then similar explanation holds good for any other thing. So let us say for like that it has come from one state to another depending upon in and out, and thereby gradually takes, right? So, but mind you, everything happens at every clock pulse, right? And clock is too fast a thing to go in a system. Suppose the it works in 100 megahertz. Even in FPGA you can have 100 megahertz, right, depending upon the device. And A6 you can even touch 300 megahertz or even beyond, depending upon the technology, such as say 0.09 technology right now. So with that you can have different speeds. So, but for these applications, that may not be a desirable thing, right? And this completes this application as such. And before we wind up, we'll see what assignment we can have on this. See, we have seen this input in this fashion, but at what time should the input be valid? That is the question, right? How are you to feed the inputs? You get my point? So you have to feed well in advance before the clock strikes. That's before the positive edge of the clock. You should have fed this, and mind you, every clock you have to feed that different inputs. 1, 1, 1, 1. All should keep track of the clock speed. At every clock you should change this. So it is a humanly impossible thing to do that. So what we can do is, you can mix. We have already seen how to use the shift register in the previous example, parallel to serial conversion, right? So that's precisely is a very handy thing application here, isn't it? So you as a user can get give, let us say, 16 bits and put it in that other module what we have already done, and then serialize, and that serialized pattern is what is applied here, right? So is that clear? And when we write the simulation, we will not go to that depths. We will show you that it can be done much more simple in a simpler fashion, right? Because of the tools, the power of the tools, right? And notice that this whenever 0, you have one output here, which you can easily trace and convince yourself at that precisely at that point of time you have this. And this can be verified very easily once we take the simulation of this later on.